So that was the last thing that we finished. Yesterday, the theorem about the perpendicularity of the level curves in the gradient vector. Okay. However, if you look carefully, you will discover the theorem. You will discover that all the visualization, all the pictures aside, it is not about level curves. Take a look at it. Well, you can see level curves aren't even mentioned. So, do you see the difference?
Here.
So what we're saying if a parametric curve remains constant as you move through its space. If the function remains constant along this the path of this parametric curve, then the tangent of the parametric curve and the gradient will be perpendicular. It is illustrated with a picture over here, but the assumption is there is an assumption about the space. What's the assumption about the space? Assumption. Not in the theorem. It is in the pictures. The assumption is that n equals 2. So we're talking about the plane. We are not talking about the plane. We are showing the plane, but the theorem itself does not have any limitations on the dimension. Okay, look at it. So it's a parametric curve, function of several variables. X is capital, so we can just say x is in Rn. It doesn't have to be in R2. So at the very least, it could be in the three-dimensional space. So let's just take a look at what the pictures would like. Same theorem. What the pictures would like when we if our space was three-dimensional, our function is of three variables. Then that picture on the right will not be a curve. It will be a surface, right? So we would be speaking of the level surfaces. Okay, so it might look like this. Okay, and we still have a point somewhere, and let me plot that this is being the parametric curve that goes along, say, what is it, x equal f of t. Okay, a parametric curve that goes along that level curve. There is a very different picture, however, now because there is so much room for our parametric curve. So we still have a point of interest here, but now there is no restriction on the parametric curve. If you think about it, if you have a curve, in how many ways can you follow that curve with a parametric curve? And primarily it's the two main directions, the one way and the other. Because we are not allowing, remembering the theory, we're not allowing this one, the derivative to be 0. So assuming the continuity of the derivative, which will remain either it will continue on in the same direction. In the meantime, with the parametric curves on the surface, it might look way more complicated, like this. It appears that we have many more options to choose from for the parametric curve. So once again, this is my A. This is x equal f of t. This is either here f is constant, and this is still f is constant, except now it's three-dimensional. So it's like what is u is equal to f of x, y, z. That's the illustration, the last illustration. The previous one is z equal f of x, y, or something like that. Okay, and then the claim is that there is still only one vector per point as far as the function of three variables is concerned. It doesn't change anything as far as the nature of the derivative. So remember, the only difference is that the derivative of a function of three variables will be a three-dimensional vector field, but that's all. So at every point there will be a vector. okay, rather than three-dimensional vector in three-dimensional space. Okay, so we didn't have a lot of discussion of that. It's fairly hard to visualize, but you can imagine once again the motion of air through space. Every particle is moving in a particular direction, and then so it fills the space with those arrows. Okay, so that's what we're looking at here, and so that doesn't change, but the level curves do change. They're not level curves anymore; they're level surfaces. And then they are also filled with parametric curves, but you can do it in a number of ways. And you can think about, say, the surface of the Earth. And suppose we're talking about, say, our function is the magnitude. What would be the magnitude of the gravity of the gravitational force? So which declines as we move away from the origin. Depends only on the distance to the center of the Earth. So it will be, its level surfaces will be concentric spheres, okay? And then what we're saying here is, well, one thing is obvious. It is when it is sphere, it is obvious, right? So we know that it's well. So the gradient vector field will be pointing in the direction, just like over here, in the direction of the nearest level surface, which means that we'll be radially pointed out with it. We'll be pointing in, right? The gradient is pointing in the direction, as we'll see, in the direction of the fastest growth, so it will be pointing towards the center of the Earth. In the meantime, so then we're concluding what that theory says, is that as we're moving on the surface of the Earth, that we take our height around the Earth, then our tangent line now, or tangent vector, if you like this. Ooh, how did it become yellow? Okay. It's tangent vector, which is, so this was supposed to be f prime of A, will be perpendicular. So it is a three-dimensional situation now. Okay, but it's still perpendicular. So in other words, it's kind of hard, easy to visualize. You can think of yourself on the surface of the Earth. This is your head is pointing up, so you're walking upright, and then it doesn't matter how you go, as long as you stay on the surface of the Earth, your direction of motion will be perpendicular to the direction up, to yourself. So if you see you working upright, and then the direction will be perpendicular. There will be a third direction, right? That we certainly could. We have talked about if you want to curve turn left or right. That's a separate issue, but that part will not change. Okay, so you will always be that angle will remain 90 degrees. Okay, so that's the idea. Okay, so as you can see, this is applicable to all dimensions. In dimension, so you can, it's not to be visualized in dimension beyond 3, so, but still everything still works out, so the ideas still work. The perpendicularity, the vector fields, four-dimensional vector fields, the perpendicularity of those vectors remains, still makes sense in dimension 4, and so on. The only thing, I suppose, well, it doesn't produce anything interesting so that we can see. Okay, so now the next topic is not this, but rather what we just started with is gradient vector fields and Clairaut's theory about the mixed derivatives, and they are equal to each other whenever the function itself, or the two functions are well, if the function itself you start with f is has enough differentiability in it, okay? Let's just put it this way, say a polynomial, any kind of combination of easy functions, there is nothing to worry about. Then the mixed derivatives over there at the top, mixed second derivatives will be equal. Okay, so that is not really, doesn't make our life easier, so we have fewer derivatives, but really not very helpful. But it helps us with gradient vector fields. So know which one of the vector fields come from as gradients, or those that do not. So this is the example so you assume that you have a vector field, and then you assume, suppose that this suppose it is a gradient vector field, then you can verify whether or not those derivatives will be matching. So you are with the vector. So this is the question or the assumption that we make, or not making assumption. Well, we make this assumption that the vector field is the gradient vector field. It is the gradient of a function, which moves us up towards f. And then Calaro's theorem takes us all the way down, and then under this assumption, then the mixed derivatives have to match. Okay, so if they do not match, our assumption was wrong. So that's exactly what has happened over here. It was a pass for that radial vector field, okay, but for this rotational vector field we started with, the answer was no. So this is fail. Okay, so fail. So our assumption that our vector field is a gradient vector field failed. Okay, so and then at the end we stated conclusion in a more general form. So a general vector field, dimension 2 specifically, and the partial derivatives are assumed to be partial derivatives of those two functions of the variables, p and q, the components, are assumed to be continuous. Then Calaro's theorem applies, and under the assumption that V is a gradient vector field, this condition has to be satisfied. That is literally the condition of Calaro's theorem. So in this diagram over here, these are P and Q over there in the middle, and then we are going down, and we are looking at. So this is let me plot the part of that theorem that is relevant here. So we're starting with P and Q. P and Q, so that's what we're starting with. And then they have, we can differentiate this one with respect to 1, this one with respect to x. And then are they equal? That's the question. So generally speaking, there is no reason whatsoever to conclude that they should be. That's all there is. Look at it. There are two functions. So this is my vector field V. These are two of its components. Absolutely arbitrary functions, P and Q. Any vector field with any two functions is allowed. Okay, so nothing suggests that this is the case. But if we assume that the gradient the field is the vector field is graded, then we add the missing pieces. So then P and Q, not just P and Q, they are the partial derivatives of some function. Okay, so that's the assumption over here. Brings extra stuff to our diagram. So it brings f, and then these are its derivatives. The P and Q are the partial derivatives of f. So this is f sub x, and this is f sub y. And if that is the case, then the Calaro's theorem would require. Well, let me erase this, because this is really that doesn't come from anything. I mean, you have two arbitrary functions, two components, P and Q. You differentiate, what do you get? Well, equal, not equal, there is no telling. But it turns out that limiting ourselves to gradient vector fields does limit the vector fields to a very narrow class, and they have to satisfy this equation. So derivative, the cross partial derivatives of the two components supposed to be equal. Okay, so before I look at some examples, let me quickly state the three-dimensional case of this theorem. So, well, let's try it. Let's a picture. So we know that the fixed derivatives have to coincide. I'll just take this diagram and make it three-dimensional. Okay. Well, I mean, I might be able to fit it here. Okay, so we have, suppose we have a vector field, B, and now it is three-dimensional, so it will be P, Q, and R. Okay? And they have partial derivatives of all kinds, so the three. Every one of them has three of them. Okay, I'm not sure that's gonna fit in. Yeah, x, y, z, x, y, z, x, y, z. Okay, so once again, this is my vector field. Three arbitrary functions of three variables make it up. Okay, So once again, no restrictions whatsoever, but suppose now that we assume that our vector field is a gradient vector field. Then these three functions are not arbitrary, but what are they? What are these functions P, Q, and R? If our vector field is gradient vector field, what do I get here?
Your partial derivatives?
Yeah, okay, so there's a function and they are partial derivatives of that function like this, right? Okay, so this is x, y, and z again. And now Clairaut's theorem still applies, even though we have three variables. We stated Clairaut's theorem only for two, but all we have to do is just do it one at a time, okay? Or rather two at a time, and so three times. Well, let's do that. So, okay, so over here, this will be f sub xx, f sub yx, and fzx, right? Okay, so differentiation, all arrows indicate differentiation with respect to that variable, x, y, z, and I do the same, and this will be, unfortunately, not doesn't fit quite well. This will be f. What is this?
XY.
F. What?
FXY.
Fxy, right. So y first, then x. Okay, then this will be fyy, not mixed. This is f zy, fxz, fyz, fzz. Okay, great. So there are 6 of them. And now pairwise, they have to be equal whenever we flip to. So let me throw out those two that we don't care about. The non-mixed derivatives are gone. They are not part of the Clairaut's theorem. But the rest of them, we are left with 6, and they pairwise have to be equal to each other. Okay, so let's try to find those. Okay, fyx is equal to fyx is equal to what? Fxy, right? So you flip the directions, the order of differentiation. So in fact, I can plot it like this, x followed by y, or y followed by x should be the same. So these two have to be equal to each other. xz and zx. That's all the where is it? Here it is. xz, zx also equal, and finally. zy and yz, these two are okay. And so let me just write the conclusion based on those three inequalities. So the gradient vector field, three-dimensional vector field, is gradient vector field. Let me write it, and it is made of P, Q, and R. Then this is what I have. The conditions will be dp dy. Well, let me use the same colors. Stop using them. So the red one will be dp dy is equal to dq dx. Okay. The next one is the purple one. dp dz is equal to what? Yeah, what is equal to? drdx. And finally, the last one is dq dz is equal to dr dy. Okay. As you can see, a lot of work. So conditions like that multiply, and certainly it points out at the difference between the dimensions as we, well, maybe for the first time, as we progress from dimension 1 to higher dimensions, and dimension 2 or 3 higher. They all have conditions like that. They have vector fields that are otherwise well behaved, but they're not gradient vector fields. In dimension 1, every continuous function is somebody's derivative. Okay, not so with the in dimension 2. So that's one of the facts that does not have an analog in dimension 1. So I've been making that point forever, that just about everything we look at it mimics results from calculus 1. Not this one. Okay, so but really it's not the complexity of the formulas that creates that I'm talking about. I'm talking about something else that's more profound. Geometric and topological difference between the straight line and say a plane. Okay, they are just different, as we'll see shortly. But let's take a look at. I'll go back to dimension 2. So the theorem. So this is dimension 3. So this is a version of dimension 3. Now I'll go to dimension 2, which is way simpler. So we don't have to worry about that. And once again, the example that we started with, this is the big one. The rotational vector field is not gradient. So rotational, I informally call it. The rotational vector field is not gradient. Okay, so once again, it looks like this. Okay, so 0 in the middle. Okay, but these are longer, but still rotation. So specifically, the one that we had was vxy equal to y negative x. Okay. So, now interesting thing is, what if we normalize it? Well, so the answer is no. It is not a gradient. What if we normalize it? Normalize means that we make all vectors unit vectors. But not changing the directions. So what's going to happen is that, suppose these are length 1, so I'll keep these, but this will become shorter. So there will be like a circular kind of a path of arrows of the same still unit length going around. And it doesn't matter how far you are from the origin, they will all have the same length. Okay. The trouble, however, that is important, is there will be a hole in the origin because it's undefined. So undefined at 0. Okay. So the vector field, let's say W, is equal to V divided by the magnitude of V. Okay. So in other words, it's y negative x divided by the magnitude of y negative x, okay, which is, what is it? So if I just keep this y negative x, so it will be 1 over, what is it? What's the numerator? Denominator? The magnitude of this vector?
Square root of y squared plus x squared.
That's right. Okay, so in other words, by the way, it's simply the distance to the origin. Okay, and now we are pursuing the same question. It's a new vector field, so it may or may not be a gradient vector field. So well, let's go on and let's differentiate. So we're going to differentiate. So let me write it out. It will be the y divided by x squared plus y squared square root, and the other one is negative x divided by x squared plus y squared square root. Okay, so that's our new vector field, and so this is P, this is Q, and we're gonna differentiate to verify those conditions of the theorem. Okay, so I'm gonna do dp dy. Okay, so, all right, so I'm gonna be doing the quotient rule. So it will be, what is it, 1 times the derivative of y times x squared plus y squared, the denominator, minus y times the derivative of the denominator, which gives me what? It gives me, with respect to y, so it will be y over x squared plus y squared. Squared. Yes. Yes. Over x squared plus y squared. No square this time. Oops. Okay, like this. Okay, so, and then the other one. dq/dx. Is this, does this look right to you? X. This y, and then y, and then 2y, y is here. Y is here, and then differentiation for y. Okay, that seems right to me. Okay, so I think it is okay. Well, anyway, let's finish the computation. Now I'm doing a differentiation with respect to x of the second components up here over here, and so I'm going to have once again 1 the derivative of x with respect to x, square root of x squared plus y squared, minus x, the numerator, and the derivative of the denominator will be x over square root of x squared plus y squared. Over x squared plus y squared.